pull up a chair, maybe dim your screen a little bit, and just, settle in.
It really is the perfect vibe for this kind of topic.
Yeah, because there's this very specific kind of quiet that happens late at night when you're just staring at a monitor, waiting for a response.
Right, just you and the machine.
Exactly. You type a prompt into a chatbot, hit enter, and there it is, that blinking cursor.
The anticipation.
And then, word by word, an answer just starts spilling across the screen. Welcome to this deep dive. Tonight, we are unpacking exactly what is happening behind that cursor.
We're taking a look at the transformer decoder.
We are. And for you listening, especially the software engineers tuning in who really want to get under the hood, our mission today is to build a rock-solid mental model of the mechanics here, how large language models actually generate text.
Because, we've spent time previously exploring how AI models read and understand text, which is an incredibly powerful capability on its own.
Yeah, the encoder side of things.
Right, but understanding is really only half the equation. Generating language, actually writing it out natively, is a completely different, and I'd argue, much harder engineering challenge.
So if the encoder part of a model is the reader, right? The part that can process an entire document all at once, taking in the full context from start to finish in a single glance.
Which is an amazing trick.
It is. But if that's the reader, the decoder is the writer. And writing is bound by one strict, absolutely unbreakable rule.
You cannot see the future.
You cannot see the future.
That constraint, that inability to look ahead, is the defining characteristic of everything we're going to cover today.
Right.
When a model is generating text, it does not have the complete output yet. It has to build it, literally piece by piece, token by token.
And the technical term for this, for the engineers listening, is autoregressive generation.
Autoregressive, yeah.
You start with token 1. Then you choose token 2 based on token 1.
Yeah.
Then you choose token 3 based on tokens 1 and 2.
And so on.
But you absolutely cannot look at word 10 to decide what word 3 should be.
Because word 10 doesn't exist yet. It simply doesn't exist in the universe.
It's total blank.
If we connect this to a human experience, it's very much like writing a group story. Imagine you're sitting in a circle and a piece of paper gets passed to you.
Okay, I'm visualizing it.
You can read everything that every person before you has written. You have perfect context of the past.
Right, the whole history of the document.
But when you put your pen down to write your single sentence, you have absolutely no idea what the person sitting next to you is going to write after you finish.
You are just committed to a relentless left-to-right process.
Exactly. You can try to set up a joke or, steer the plot a certain way, but you're blind to what comes next.
So mechanically speaking, how does the architecture actually enforce this? Because in our previous deep dives into the encoder, we established that tokens look in all directions to gain context.
They do, yeah, bidirectional attention.
But the decoder obviously can't do that, which brings us to masked self-attention.
Right, because if the decoder could see future tokens during training, it would be cheating.
It would basically have the answer key.
Exactly. It would be using information that simply wouldn't be there when it's out in the wild generating real text. So, the engineers introduced the attention mask.
And if I'm visualizing this mathematically, isn't this basically acting as a triangular matrix? Like it explicitly blocks those future connections.
It is, and the math here is beautifully simple, but it's ruthless. When calculating the attention scores, which, determine how much focus one word should place on another, the system takes all the positions that represent future tokens.
Okay.
And it sets their raw scores to -infinity.
Wait, -infinity. Doesn't that just completely break the math? Like, does it ignore those future words entirely? Or is there some tiny residual memory lingering in the system?
No, it ignores them entirely. There is zero residual memory.
Wow.
Because the very next step in the neural network is a softmax operation.
Right, which normalizes everything.
Softmax turns raw, unbounded numbers into probabilities between 0 and 1, so they all add up to 100%.
Okay.
When you feed -infinity into a softmax function, the resulting probability is absolute 0.
It's just gone.
Those future positions are entirely zeroed out. They become mathematically invisible.
So it's like putting a solid brick wall to the right of each token. You can look to your left all you want, seeing everything that has already been generated, but you absolutely cannot see through the wall to the right.
That's a great way to put it. And what's fascinating is how this plays out during the training phase.
Because training has to be different from generating.
Bro, Vastly different. You might assume that because generation is strictly sequential, training the model must also be painfully sequential.
Which would take forever.
Exactly. So engineers came up with a brilliant illusion to bypass that. During training, we actually feed the entire target sequence into the decoder all at once.
To maximize the GPU efficiency.
Right. But because of that triangular attention math we just talked about, the computation at position 3, for example, is strictly prevented from accessing positions 4, 5, or 6.
Even though they were sitting right there in the hardware memory.
They're right there, but mathematically inaccessible.
So it's a massive parallel computation happening on the silicon, but the mask enforces a sequential reality for every single token simultaneously.
It is an incredibly elegant trick. It's really the core innovation that makes training massive models at scale even possible.
Because without that parallel illusion, iterating on these architectures would take lifetimes.
Literally centuries of compute time.
Okay, so we have this writer, the decoder, sitting there with its brick wall, only able to look left. But if we go back to the original transformer architecture, the one built for translation tasks.
The 2017 paper, yeah.
Right. The decoder isn't working entirely alone in that setup. It needs to know what the reader, the encoder, actually read. And this brings us to the concept of cross-attention.
Cross-attention acts as the bridge between the reader and the writer.
Okay, lay that out for us.
Well, in standard self-attention, a token generates a query, a key, and a value to interact with its fellow tokens in the exact same sequence.
Right, looking at its neighbors.
Well, but in cross-attention, the roles are split.
So the queries come from the decoder.
Yes.
But the keys and the values, the actual information being retrieved, come from the encoder.
Think of it like a student taking an open book exam.
I love this analogy.
The decoder is the student. The student looks at what they've written so far on the page, their own internal representations, and formulates a question about what they need to write next.
And that question is the query.
Exactly. Then the student looks over at a textbook. The textbook is the encoder's output.
The source material.
Right. The student matches their query against the textbook's index, which are the keys, to extract the right information, which are the values.
For the software engineers listening, let's elevate that to a database analogy.
Perfect.
Cross-attention is essentially a fuzzy database lookup.
Mm-hmm.
The decoder generates a query vector, which acts like a SQL search term. Right.
The encoder holds the keys, which are like indexed database tags, and the values are the actual row data returned when the query mathematically aligns with a key.
That translates perfectly. Let's ground it with a specific example just to make sure it clicks.
Okay, lay it on me.
Say the model is translating a sentence from French to English. The decoder has already written, the cat is sitting on the key.
Okay, so it needs the last word.
Now it needs the next word. It takes that current state, generates a query vector, and sends that query over to the French encoder output.
The textbook?
It scans the French sentence, finds the mathematical representation for the word tapis, gives that specific key a very high attention weight because it aligns with the query, pulls the value, and outputs the English word mat. Mat. Boom. It queries the source material to inform its next native step.
Exactly.
Okay, now I want to transition to the actual generation loop. I want the literal step-by-step process that kicks off when you hit enter on a prompt.
The entire process starts with a single seed. We use a special token called the beginning of sequence, or BOS token.
Okay, so I hit enter. Step 1, the system feeds that single BOS token into the decoder. It ripples through all the layers we just discussed, the mask self-attention, the cross-attention, the feed-forward networks. What comes out the other side?
At the very end, what comes out is a massive probability distribution over the model's entire vocabulary.
So it's grading every possible next word.
The model generates a list of predictions. Given the context, there might be a 12% chance the next word is the, an 8% chance it's I, a 5% chance it's in.
And then it rolls the dice based on the temperature settings.
Right. The system selects one of those options based on its sampling parameters. Let's assume it picks the.
So step 2, we don't just ask for the next word in isolation, do we?
No, we take our original seed, the BOS token, and we append our newly generated word, the.
We feed that entirely new, slightly longer sequence back into the very beginning of the decoder.
And it processes everything again.
The masked attention ensures the looks at the BOS token and itself. It spits out a new distribution and we pick, let's say, cat.
Then step 3. We feed in BOS, the cat.
And we get sad.
And this loop repeats. growing the sequence one single token at a time until the model finally outputs an end-of-sequence token.
Or it just hits a hard-coded maximum length limit and cuts off.
Exactly.
But wait, if you were actually processing that entire growing string of text from scratch every single time you wanted a new word, your compute costs would explode.
Oh, it would be impossible. This is where we need to dig into something called the KV cache.
The KV cache. I know this is a huge deal for anyone trying to run these locally.
Without the KV cache, this generation loop would be a catastrophic bottleneck. If we look at the algorithmic complexity, recomputing everything at every step for a sequence of n tokens requires O(n) squared computation.
O(n) squared. So it scales horribly.
Horribly. By the time you are generating token 500, you are completely recalculating the keys and values for tokens 1 through 499.
Passing them through every single neural network layer all over again.
Even though they haven't changed.
Which is a massive waste of resources. So the solution is to cache them. How does the architecture actually store that data?
As the model generates each token, it saves that token's key and value vectors in the GPU's memory.
Okay.
When it's time to generate the next token, it only computes the query, key, and value for that one new token. Then its query just attends to the neatly saved cache of all the previous keys and values.
This drops the computation at each step from O(n) squared down to just O(n).
Which is a lifesaver for processing speed.
But, and there's always but, it introduces a different kind of architectural tension. This KV cache is exactly why running a local instance of an AI model on your machine eats up your unified memory so quickly.
It's the silent killer of RAM.
You are storing massive matrices of floating point numbers for every single token in the conversation history across every single layer in the model.
And that is a critical trade-off software engineers have to manage daily. You save precious compute cycles, but you pay for it in GPU memory.
Which is often the most scarce and expensive resource in the system.
Absolutely. The longer the conversation context, the larger the KV cache grows until you eventually just run out of RAM entirely.
Out of memory error. We've all seen it. So we've been talking about this in the context of the original encoder-decoder translation model.
The classic setup.
Right. But if you look at modern AI, the tools most people use today, like GPT, Claude, or Llama, they did something radical. They looked at that dual architecture and decided to just throw half of it away.
This was the decoder-only revolution.
It's kind of crazy to think about.
It was a monumental architectural shift. They discarded the encoder entirely.
And since there is no encoder, they also ripped out all the cross-attention layers we just talked about.
Gone. You are left with a beautifully streamlined stack.
Right.
Just masked self-attention and feed-forward networks.
But wait, if there is no encoder to act as the reader, how does the model even understand the user's prompt in the first place?
This is the elegance of the decoder-only design. It treats the prompt and the generated response as one single continuous sequence.
Oh, wow. Okay, let's visualize this. You type in your prompt. All of those prompt tokens are fed into the decoder at once. The model processes them using that same causal masking we discussed earlier.
Right, the brick wall.
So token 5 of your prompt can't see token 6. It builds up a rich left-to-right understanding of your input.
And then, without switching to a different neural network, without crossing a bridge to a different component like cross-attention, generation just begins natively right at the end of that sequence.
That is so clean. It operates under a unified paradigm, the exact same architecture, the exact same weights, the exact same attention mechanism is handling both the understanding phase of the prompt and the generation phase of the response.
It simplified the scaling laws tremendously. That's why it became the dominant approach for building massive general-purpose language models.
But it raises a huge question. If these decoder-only models rely entirely on their own generated sequence to understand what to say next, how do you even begin to train a completely blank model?
It's true.
Wouldn't a randomized, untrained model just generate absolute garbage, read its own garbage's context, and get horribly confused?
You hit on a massive vulnerability right there.
Really?
Yes. If you try to train a model by letting it guess the next word and then guess the word after that, you run into compounding errors.
Because it's trusting its own bad guesses.
Exactly. If the model makes a mistake on word 2, say it guesses dog instead of cat, then word 3, word 4, and word 5 are all going to be conditioned on that hallucinated dog.
The errors just compound exponentially.
And learning becomes completely impossible.
So to fix this, engineers use a technique called teacher forcing, which I gotta say reminds me of a piano teacher sitting next to his student.
That's a great analogy.
The student is trying to learn the right-hand melody, but they keep messing up the timing. So the teacher reaches over and perfectly plays the correct left-hand accompaniment, no matter what mistakes the student makes.
The student always hears the correct context.
Exactly. Which allows them to focus on fixing their own specific errors without the entire song devolving into noise.
In a machine learning context, teacher forcing means that during training, we always feed the model the correct ground truth tokens from our training data as the context for the next prediction.
Regardless of what the model actually predicted a millisecond prior.
Right. We force the correct context.
But what happens when the teacher leaves? That creates a huge train test mismatch, right? I've heard it called exposure bias.
It is a significant pitfall. Because of teacher forcing, the model grows up in a pristine, perfect environment.
A bubble.
It only ever sees perfectly constructed sentences from its training data.
Okay.
But when we deploy it, and it's generating text for you in the real world, there is no teacher providing the correct next word. It has to rely on its own past outputs.
And if it makes a slight grammatical error or a hallucination early in a paragraph?
It has never been trained on how to recover from its own mistakes.
It's like training a GPS by constantly spoon-feeding it the exact perfect coordinates every 10 seconds. The moment you put it in the real world, and it has to rely on its own slightly fuzzy sensors, a 1-degree error starts to drift.
And pretty soon, you're driving into a lake because it doesn't know how to course correct.
Right. So how do we fix that drift in the real world?
The industry developed several alignment techniques to address this. The most prominent is RLHF.
Reinforcement learning from human feedback.
Yes.
Break that down for us. How does human feedback actually change the mathematical drift?
Well, instead of just predicting the next word, we let the model generate entire responses, making its own mistakes along the way.
You take the training wheels off.
Exactly.
Yeah.
It might generate 3 different answers to a prompt. Then, human graders look at those paths and rank them. They might say, response A hallucinated halfway through, but response B stayed on track.
Okay, so humans grade the whole trajectory.
We use that ranking to train a separate reward model, which then goes back and fine-tunes the main language model, updating its internal parameters to favor the paths that humans preferred.
And there's also DPO, right? Direct preference optimization.
Yeah, DPO is gaining a lot of traction. It bypasses that separate reward model entirely and optimizes the language model directly on those human preferences.
So both methods essentially force the model to look at its own imperfect generations and learn how to navigate them.
They teach the model how to be robust in the wild, smoothing out the exposure bias it inherited from teacher forcing.
Now, we need to confront the harsh reality of this whole system.
The speed bottleneck.
The speed bottleneck.
Yeah.
We established earlier that generation is inherently sequential. You cannot generate token 500 without token 499.
That is a hard data dependency.
So even if you have a data center filled with the world's most powerful GPUs, generating a 1,000 token response requires 1,000 sequential, entirely separate forward passes through the model.
You can parallelize the matrix math inside a specific layer, but you cannot parallelize across time. Generation is permanently tied to the ticking clock of the sequence.
Which is exactly why it feels like the model is typing it out to you in real time. Because it practically is.
It really is.
But engineers notoriously hate bottlenecks. So what are the speed hacks being used to bypass this sequential nightmare?
The most brilliant workaround is called speculative decoding.
The speculative decoding. Okay.
We know the giant model is slow because it has to evaluate every single token sequentially, hauling massive weight matrices from memory into the compute cores. So what if we brought in a tiny, incredibly fast assistant model?
Like a rough drafter.
Yeah.
How does the small model interact with the big one?
The tiny model races ahead and quickly drafts a sequence of, say, 5 candidate tokens. Because it has a fraction of the parameters, it does this incredibly fast.
Okay.
Then we take those 5 drafted tokens and feed them to the giant, slow, highly accurate model all at once.
Oh, I see where this is going. Because the giant model now have the text in front of it, it can process all 5 tokens in parallel in a single forward pass.
Leveraging that parallel illusion we talked about during training,
That's genius.
the giant model essentially acts as the expert verifier. It looks at the draft and says, token 1 is correct, token 2 is correct, token 3 is correct. Wait, the 4th token is wrong.
So it accepts the first 3 tokens instantly.
saving us 3 sequential time-consuming passes, and then it overrides the 4th token with its own correct prediction, throwing away the rest of the draft.
That is a phenomenal use of resources. You get, what, a 2 to 3x speed up?
Easily, with absolutely zero loss in quality, because the giant model always has the final say. It's verifying instead of generating from scratch.
Are there other ways to squeeze performance out of these architectures?
There are parallel decoding approaches like the Medusa architecture.
Medusa, like the snakeheads.
Exactly. Instead of a separate small model, Medusa adds extra heads onto the giant model itself, trying to predict multiple future tokens simultaneously based on the current state.
Fascinating.
And of course, there's quantization.
Right, quantization. That involves dropping the precision of the model's weights. You go from a 16-bit floating point down to 8-bit or even 4-bit representations.
Which makes the math a little fuzzier, but it vastly reduces the memory overhead.
And more importantly, it speeds up the memory bandwidth, which is often the real physical limit during generation. You can move smaller numbers from the RAM to the processor much faster.
And every millisecond of latency shaved off is a massive victory when you are running these autoregressive loops billions of times a day at a global scale.
It really is. You know, when we zoom out from all this, the matrix math, the database lookups, the caching algorithms, there is something almost poetic about autoregressive generation.
There really is, because each token the model generates is an absolute commitment.
There's no backspace key for the model during a pass.
No. The moment it is generated, it becomes part of the permanent context. It shapes the future of the entire response, and during that specific generation pass, the model cannot go back and change its mind.
It is building meaning, literally one piece at a time, completely unable to foresee what the end of the sentence will actually look like.
Which is a computational formalization of how humans actually speak.
We talk in a forward direction.
We commit to our words as they leave our mouths, trusting our internal mental models to figure out how to finish the sentence we just started.
We can't unsay what we've said, and the decoder can't ungenerate what it has generated.
It is an absolute triumph of engineering that we've made such a complex, constrained process look so simple and fluid on the surface.
It's incredible. So the next time you are sitting in the dark watching a chatbot generate a response word by word, remember, you aren't just watching a magic trick.
No.
You are watching massive, sequential forward passes. You are watching causal masking enforce the arrow of time. And you are watching incredibly optimized KV caches fight against the physical limits of silicon memory.
It's an entire symphony of engineering.
It is, and we want to leave you with a final thought to mull over on your own. We've spent this entire deep dive establishing that the decoder is locked into a strict left-to-right causal timeline. It cannot change the past.
Right.
But what would it look like if we built a completely new architecture? What if we designed a language model that was allowed to iteratively go back in time to silently revise and edit its own past thoughts before it finalized a single word on your screen?
Now that is a wild concept.
What kind of intelligence would that look like? Think about it. Until next time.